So, good evening everyone. So, we're going to solve the shear and moment for beams. So, in our given diagram, we have three loads. We have two loads for compressive loads. These are compressive loads, and we have a uniform load. So, these loads have a force of the downward force. You have first compressive load is we have force of 30 kilonewton, and second is we have 50 kilonewton, and third is the uniform load, which is 20 kilonewton per meter. So in order to draw the shear and moment diagram, we're going to solve it using the area method. So in order to solve the area method, we're going to find first the reactive forces of B and D, which is RB and RD. So in order to find the reactive force for RD, we're going to apply moment at B in a clockwise direction. So we have negative RD times 7 meters from B to D plus 50 kilonewton times 4 meters from B to C plus 20 kilonewton meter, which is our uniform load, times from B to D, which is 7 meters, times 7 over half to get the moment arm of the concentrated load, minus 30 times 1 because it is counterclockwise in direction. Then, in order to find the reactive force of RB, going to have a summation of forces along the y-axis, vertical axis, since we have the value for RD, which is 94.286 kilonewton. So summation of forces along the vertical axis or y-axis is equals to 0. So our RB is going upwards, then it is positive, plus our RD, which have the value of 94.286 kilonewton, going upward, so it is positive, then minus 30 going downward, then our C minus 50 going downward, then uniform load minus 20 times 7 meters from B to D equals to 0. Then our reactive force for RB is equals to 125.714 kilonewton going upward. So since we have the forces for our reactive forces, we're going to draw our shear diagram. So in order to draw our shear diagram, we're going to get the shear load. So in this load, we have only negative 30 kilonewton going downward. So our shear load is negative 30. So from A to B, since there is no shear load at from A to B, so that is why we have also a negative 30. So for shear load at B, since we have a shear load for B, we have the value for RB, our reactive force, which is 125.714 kilonewton. That's why we're going to add negative 30 then RB to get our shear load for B. So since it is positive, that's why we're going to write it above. So next we're going to get the shear load from B to C. So in order to get the shear load out of from B to C, since from B to C there is a shear uniform load which is going downward, which is 820 kilonewton per meter. So we're going to write for an equation of VBC is equals to the shear load for B, which is 95.714, then minus, because it's going downward, the forces, the uniform load forces going downward here, so minus 20. So we're going to find the area on this only, so we're going to multiply it by 4 meters. Then going to compute this, it will result with this value. So since it is 15.714, then we're going to put this below of 95, so this. After that, we're going to get the shear load for C in this line at the side along C. So in order to get the shear load of the C, since we have a 15.714 from B to C, then we have a compressive load going downward, the force is going downward, which have the value of 50 kilonewton. You can write it as an equation of BC is equals to 15.714 minus 50. Then if you're going to calculate, the value for this is negative 34.286. It is negative because it is going downward, the force in there. And then from the force in there, there is a shear load, which is from B to C 15, which is 15.714. That's why we can come up with this equation. So since it is negative 34.286, so we're going to write it below the line, negative 34.286. The next, we're going to get the shear load from C to D. So as you can see, there is a negative 34.286, and from D there is also a uniform load having a force of 20 kilonewton per meter. So since it is downward, it is negative. So we can formulate an equation of shear of C to D is equals to negative 34.28286 minus 20 times 3. Since we're going to get the area only for C to D, that's why we're going to multiply it by 3. we're going to multiply our force by 3, then adding with this value for our C. Then if you're going to calculate this one, the answer for this one is negative 94.286. Then since it is negative 94.286, you're going to write it down below in here, negative 94.286. Then the last, we're going to get the shear load for our D line, this line D. So since we have a shear load of we have the value for our shear load from C to D, which is negative 94.286, then we have of course the value for our reactive force RD, which is 94.286 kilonewton going upward. So since it is positive, and we can formulate equation for our shear load, which is that negative 94.286 plus our value for our reactive force, which is 94.286 kilonewton. Then we have the value for our shear load at D, which is 0. So since we get the shear load of each section A, B, C, D, for line A, B, C, D, we're going to draw the diagram. We're going to trace it like this. Then going to shade it. So we have area 1, then we need to shade this part. This is our area 2, then shade this part, and you can get our area 3 for our shear load. So this area 1, 2, and 3 are very useful in getting our moment diagram. So let's see in the next video. So in order to get the moment of A, B, C, D, we're going to solve first our area for 1, 2, and 3. So for area 1, since it is a square or rectangular, so we have a formula for area, which is base times height. So our base is 1 meter, then times the height, which is 30. Then our area 2, which is, since it is trapezoid, we have a formula of 1/2 times the height of 95.714 from this side, and plus the height of the right side, which is 15.714 times the base, which is 4 meters. Then our area for number 3, since it is trapezoid, then we're going to copy the height. We're going to add the 34.286 and 94.286 times or multiply for the base, which is 3 meters. So our area for this 3 and this 2 is 1. Area for our 3 is 192.858 meters. So since we have our area for our area 1, area 2, and area 3, we're going to get each moment for A, B, C, and D. So our moment for our A, so as you can see here, there is no applied moment or a reaction moment in this along side of A, so it is 0. So moment of A is equals to 0. Then from B, moment for B, since it is 0 from here, from A, then to B, from B to the B, moment of B, there is a area which is 30 in this side. Then since it is negative, that's why our moment for B is negative 30. So 0 from moment to A, then minus 30 since it is negative downward from our beam. That's what it is equals to negative 30. Then our moment for C, since it is negative 30, so for the moment of C from negative 30 to C, which have the area of our 2, which is equals to 222.856 meters. So we're going to add the moment of B, which is negative 30, plus the area from B to C to get our moment for C. So negative 30 plus 222.856 is equals to 192.856. Then I'm going to get the moment for D. So from C to D, with respect to our area in this, we're going to add our moment for C and the area from C to D to get the moment for our D. So 192.856 in our area for in this side is 192.858. So it is minus because it is the area is in down or downside or going down, unlike the area of 2, which is the upward of the node, since it is at the top or if the upward. Since we're going to talk about upward, it is positive, then downward it is negative, just like in this. That is why it is negative 30 in our moment for B. So let's back of moment for D, then 192.856 minus the area 858. Then our moment for D is equals to 0.002. So since we get our moment for A, B, C, and D, and we're going to draw the diagram. So from moment of A, downward from -20, then upward to 192, then downward again, because in this axis it is 0, then 0.02, then downward again, and going to shade this area. So this is our shear and moment diagram, our shear diagram and our moment diagram. So that's all for this video, and thank you so much for listening, and I am sorry for my voice also. God bless us all. Bye.